Let's tackle example 1, heat flow in a rectilinear slab. We have here a copper plate that's a centimeter thick, and it has dimensions 5 centimeters by 15 centimeters. The bottom surface of the copper plate is in contact with an isothermal heat source that's at 40 centigrade, and the top surface of the copper plate is in contact with a printed circuit board that's isothermal at 20 degrees centigrade. So the first thing we notice about this question is that it's actually asking us for heat. How much heat must be supplied? And so that's a trigger to us to use Fourier's law. We'll see in upcoming examples that when a question asks about a temperature profile, generally in that case we'll use the heat equation. All right, so Fourier's law we've just learned. It's heat equals negative K dt dx. And what we want to know is this value Q, or more specifically, we want to know, rather than heat flux, we want to know heat flow. So that's Q over A. So a quick way we can calculate this is to integrate the equation. So we'll pull our area over to this side. And we can integrate both sides of this equation so long as Q is constant, so it's not dependent on x or t, and K and the area are independent of x and t. And we'll make that assumption. So if we integrate, we'll start by drawing an x-axis onto this plot. And we'll say that at this point, x equals 0, just because it's convenient. And we'll define the x-axis to increase in this direction. I'm going to convert the units right now from centimeters into meters because our thermal conductivity is going to be in units of watts per meter Kelvin. So we'll integrate from 0 meters to 0.01 meters. And that is, again, the thickness of this copper slab. In terms of temperature, we're integrating from 40 to 20 centigrade. In this case, it doesn't actually matter whether we use centigrade or Kelvin because it's only a difference in temperature. But for good practice, we'll use the correct units. Okay, and if we do that, we now have Q times 0.01 meters equals negative K A times 293 Kelvin minus 313 Kelvin. So we need to know our area and our thermal conductivity. The thermal conductivity we can look up for copper. For copper, that's 400 watts per meter Kelvin. And the area we can calculate, 5 centimeters. Actually, we'll just convert this straight away to units of meters. 0.05 meters. Times the other dimension is 0.15 meters. And that gives us our area. So what we are after, again, is this value of Q. So we plug in all these values. There's our K, our area, our delta T, which we'll note is negative. And because it's negative, it will cancel with the negative out front here and give us a positive value of Q, which basically means that heat is flowing in the direction of our positive x coordinate, which is exactly correct. All right, and I calculated this to be 6,000 watts. So that's quite a bit of energy required to keep this copper slab isothermal. Thanks for watching.